Hi, and welcome to Gravitational Fields Lesson 5a. Today is a relatively short one, but we've just got two really important graphs, and because they're so important, we're going to go really slowly and make sure we fully understand what both of them are saying. So what we have here is a graph of how force and potential change with little r. Remember what little r means? Distance from the centre of the planet, as opposed to big R, which is the radius of the planet. In the first video, I'm going to look at the shape of the graph once R is greater than big R. So what happens when you're outside of the surface of the planet. Then in the second video, we're going to be looking at this little bit of the graph here, what happens once you go underneath the surface of the planet. Now the first thing you may notice about both these graphs is I've defined them in the negative. Now one of them has to be negative. Which one is it? That's right, the potential graph has to be negative. The force graph depends which way you define it, it's just a vector, we can define it as positive or negative. Doesn't really matter. Okay, what I'd like to do for now is just pause the video, sketch out these axes and see if you can draw the graphs from big R to little r on both of these, so just that part of the graph. Pause it, have a go. Okay, well what are we expecting? Let's start with force. We know that the force is going to be some value at the surface. Let's just put that in there. And it's going to get smaller and smaller and smaller as we go further and further away, trending towards zero at infinity, because once we're infinitely far away from the planet, we're not going to have any gravitational force on us. It's actually going to be an r-squared dependency because we know that from our equations. So therefore, we're just going to get a nice shape like that, curving off towards zero. Okay, now let's think about the potential. The potential has some value, again, at the surface. Easy enough. Now we think back, how do we define gravitational potential? Well, we define it as zero at infinity. So again, we're going to have to go off to zero at infinity. Now this is just a 1 over r shape, but in fact they're pretty similar. So again, this is just going to arc off like that. So what else can we do with these graphs? Well, we know the field strength is the differential of the potential. And whenever we've got one of those relationships, that allows us to do a couple of neat things. Firstly, that means that the area under this graph is going to equal the change in potential energy. Similarly, if we take a point and we do the gradient of that graph, that's going to equal the force or the g field, depending on how you're defining it. So if we differentiate this, we'll get this, and if we integrate that, we get that, which is exactly what you'd expect from this relationship. Okay, what I'd like you to do now is I would like you to think about what's going to happen to the force as we go back down to r equals 0. And remember, r equals 0 is the centre of the planet. So what's going to happen to the force as we go down to r equals 0? And what's going to happen to the potential as we go down to r equals 0? Have a think, have a go yourself, and I'll tell you in the next video.